In this lecture, we will find two types of cubic splines that pass through a given finite number of points. We will show a programming example to find the two different types of cubic splines. For the programming part, we will use Mathematica. By saying that we will use Mathematica, we will not use the built-in interpolating function commands in Mathematica. There is a method that uses the second derivative values at the different points as the unknowns. We will not employ that method here. The 4 points through which we will fit the cubic spline curves are 1, 0, 2, ln 2, 3, ln 3, and 4, ln 4. The two types of cubic splines that we will be looking for are the natural cubic spline and the clamped cubic spline, with specified values for the first derivative at the leftmost and the rightmost endpoints. We designate the first point to be x sub 0, y sub 0, so that 1, 0 is equal to x sub 0, y 0. x1, y1 will be equal to 2 ln 2. x2, y2 equals 3 ln 3, and x3, y3 equals 4 ln 4. The first part of the Mathematica code is what we will refer to as the initialization part. This is where we input the x and y coordinates into Mathematica. For this lecture, we will separate the x and y values into two separate lists. The first list, which we call x values, will be the list of x coordinates. And so the list x values is made up of 1, 2, 3, and 4. Observe that we had put decimal points after each value. The reason for this is that we want Mathematica to carry out the calculations as floating point calculations. We feel that floating point calculations in Mathematica tend to use less memory and are carried out faster than if we were to use exact values. We designate the list of y coordinates as y values. The notation that Mathematica uses for the natural logarithm function, ln, is uppercase log. And so the set of y values that we input into Mathematica are 0, uppercase log square bracket 2, uppercase log square bracket 3, and uppercase log square bracket 4. Observe that we are not using decimal points for y values. That is because we are hoping that the decimal points in x values will be enough to toggle Mathematica to use floating point calculations. Now we have a total of 4 points, and so we define the variable number of points. Just one word, and this is equal to 4. Now Mathematica starts its indexing at the index 1. With the way we are indexing the points, we start our indexing at 0. For this lecture, the last point x sub 3, y sub 3 is supposed to be x sub n, y sub n. And observe that n is 1 less than the number of points. And so we define n to be equal to the number of points minus 1. Now, the mere act of typing these lines of code on screen does not input x values, y values, number of points, and n into Mathematica. We have to evaluate these lines of code. In order to do that, we press the keys Shift and Enter together, and we have inputted all of these values into Mathematica. We know this to be the case by this input symbol at the start of the lines of code. We also have an output. The output is equal to 3. It corresponds to n. It is the only line of code that does not end with a semicolon. Each of the other lines of code that ends with a semicolon does not produce an output on screen. The values are merely stored in Mathematica. We'll put a semicolon at the end of the last line. and evaluate by pressing Shift and Enter. This suppresses the on-screen output. Now, even though we have separated the x and y coordinates, we will still have to reindex them. This is to make it more in line with the way we are indexing the points. We are also hoping that this will be less confusing. For this, we are going to use what is called a do loop. Now, we will be reindexing the x and y coordinates separately. That is two tasks within the do loop. And so we open with a curly brace, just as we do when we're listing the elements of a set. After all, we have two elements in the set of tasks. We will use the variable $x for the reindexing of the x coordinates. Now, Mathematica has its own indexing protocol. For example, let's take a look at x values. It's a list of objects. Mathematica automatically indexes these objects. And so the value 1 is actually x values sub 1. Mathematica starts its indexing at the value 1. Recall that we start our indexing at 0. And so we have this issue like we had with number of points and n. And so we index $x within the do loop as square bracket k minus 1. Another thing that we should point out here is that we are using $x for the actual x values. We will use the variable $x for the variable within functions. To the Mathematica variable $x sub k minus 1, we assign the value x values, and we use the indexing that Mathematica uses. We use double square brackets. Now the index for x values is 1 more than the index for $x, and so the index for x values is k. And we close with 2 square brackets. We provide a comma after this line of code because we have 2 tasks within this set of tasks. The next task, which is for the y values, we just use double y. That is, we simply replace the x's by y's. And so we have double y sub k minus 1. And to this we assign y values double bracket k. Now we have both tasks, and so we close with a curly brace. We only need to tell Mathematica from what value of k to what value of k Mathematica has to do this. K is the index for both x values and y values. And so k starts from 1 all the way up to the number of points. We're done with all the commands that go inside the do loop, and so we just close this with a square bracket and evaluate by pressing the Shift and Enter keys together. Nothing happened except that we know that the x values and the y values are stored in $x and $y because of this input symbol. To verify quickly that the x values and the y values are indeed stored in $x and $y, we use the Mathematica command table, which will make Mathematica show on screen the x and y coordinates. So we type table, square bracket, curly brace, $x sub k, comma, $y sub k, and then close with the curly brace. And I would tell Mathematica to show the coordinates from k equals 0 through n. This time we are starting k and ending k with the indices that we are actually using for our coordinates. We press the Shift and Enter keys and get the listing of the points. Well, we don't really need to see the table command and the output, and so we delete the table command and the output. The next step now is to define the different polynomial segments. Each polynomial segment, which we call uppercase b sub k of x, is equal to a sub k times the cube of the quantity x minus x sub k plus b sub k times the square of the quantity x minus x sub k plus c sub k times the quantity x minus x sub k plus d sub k. And this is for k going from 0 all the way up through n minus 1. The indexing with k going from 0 through n minus 1 is a hint that it might be a good idea to use a do loop. We copy the definition almost as is into the do loop. There is only one line of command, and so we don't need curly braces for this. So we start with uppercase P, square bracket K for the index. And then for the variable x, we open with a square bracket x. And since x is a variable and not an index, we put an underscore right after x. And then close with a square bracket. We put an underscore after the variable of a function and only at the time when we are defining the function. To write down the actual code, we virtually copy the formulation of p sub k. P sub k equals a sub k, and so we have a square bracket k times the quantity x minus x sub k. X sub k, of course, when we write it in Mathematica, is double x square bracket k. Cube this quantity, and then we have b sub k times the quantity x minus double x sub k, square that, plus c sub k times the quantity x minus double x sub k, and then we have d sub k. We finish the do loop by indicating that k goes from 0 through n minus 1. We evaluate this line of code by pressing Shift and Enter. We can check to see, for example, what some of the polynomial segments would look like. For example, let's take a look at p sub 2 of x. We type uppercase P square bracket 2 square bracket x. We don't need the underscore for x here. Press Shift Enter and we see the polynomial. Next, we tackle the unknowns. These are a sub k, b sub k, c sub k, and d sub k. It's a list of unknowns, which we simply call uppercase unknowns. For this, we can use a do loop again, but this time we're going to use the table command. Each polynomial segment has a list of unknowns, and so we write these unknowns as a list inside the table command. And so we have open curly brace, a sub k, b sub k, c sub k, and d sub k. And k goes from 0 through n minus 1. We press Shift Enter, and we get the list of unknowns. Upon closer inspection of this list, we observe that we have these inner curly braces. Having these inner curly braces can run into all sorts of conflict when we use the solve command in Mathematica. So we have to get rid of every inner brace within the unknowns list. So we use an afterthought command. We type / after the code for the unknowns, and we use the mathematical command flatten. We press Shift Enter again to evaluate, and now we don't have any inner braces within the list. We'll put a semicolon at the end of this code to hide the list. We now get started writing the different equations for the unknowns. The first set of equations are the node equations. For the node equations, we use the table command again. We have d square bracket k, and because what we have here is an equation, we use a double equals. d sub k is double equals y square bracket k, and k goes from 0 through n minus 1. We still have this extra equation, and for this we create a list of a single equation. Now this equation is for the rightmost endpoint, and so we call it right endpoint node. It's a list of one equation, and so we start with an open curly brace, p sub n minus 1 of double x sub n, double equals double y sub n. We evaluate these lines of code just to make sure that the lines of code actually do work. And now that we know that they do work, we put semicolons at the end of each line, reevaluate, and hide the output. Next, we have the continuity equations. For this, we will use the table command. And so we write table of p sub k of double x sub k plus 1 double equals p sub k plus 1 of double x sub k plus 1. We just check to make sure that all the brackets are paired up and indicate that k goes from 0 through n minus 2. We evaluate this line of code to see if it works. And there it is. We put a semicolon at the end of the line to suppress the output. Then we have the first smoothness equations, which are the first derivative equations. These equations are very similar to the continuity equations, and so we just copy the code for the continuity equations and simply put primes for the functions. We remove the semicolon at the end of the line and evaluate just to check if the line of code works. Then we suppress the output. Except for the double primes, the second derivative equations are exactly the same as the continuity equations. And so we simply copy and paste the continuity equations and add double primes to the functions. We remove the semicolon to test the line of code. And seeing it works, we bring back the semicolon to suppress the output. The first type of spline that we're supposed to look for is a natural spline. We write down the equations for the natural spline, and these are simply p sub 0 double prime of double x sub 0 equals 0, and also p sub n minus 1 double prime of double x sub n equals 0. And don't forget, we have to use double equals here. We evaluate this line of code, put a semicolon at the end to suppress the output. The second type of spline that we're supposed to look for is a clamped spline. For the exercise, we have cube prime of x sub 0 equals minus 10. And so we write down p sub 0 prime of double x sub 0 equals minus 10. The second condition for the clamped spline has the first derivative at the rightmost endpoint equals minus 20. And so with p sub n minus 1 being the last polynomial segment, we write down p sub n minus 1 prime of double x sub n double equals minus 20. We test this line by evaluating, then put in a semicolon to suppress the output. To get started with solving the equations, we put all the equations for each of the cases together. We put all the equations together and collectively call them all equations. All equations is a set of equations. The first set is node equations. This is followed by the equation at the right endpoint node. Then continuity equations, followed by first derivative equations, and then second derivative equations to round out the core equations for the splines. We are going to solve for the natural spline first, and so the last set of equations in this list is natural spline. We evaluate this so that all equations get inputted into Mathematica. And here are the equations. Again, we have these inner brackets within the output. We've said before that these inner brackets can run into conflict when we use solve within Mathematica. We use the command flatten to get rid of these inner brackets. evaluate, and so all equations now does not have any inner brackets. Again, we suppress the on-screen output for all equations by putting a semicolon at the end of the line and evaluating. So to finally solve for our first cubic spline, we type the command solve uppercase S-O-L-V-E. What are we solving? We are solving the system all equations. What are we solving for? We are solving for the unknowns. Evaluate, and here are the different coefficients. To find the coefficients for the clamped spline, all we have to do is change natural spline in all equations to clamped spline. We evaluate this to make sure that the system of equations for the clamped spline gets inputted into Mathematica. Then we go back to the solve command and re-evaluate the solve command, and we get the coefficients for the clamped spline.